Okay, sorry about the technical issues. So, okay, so this is the overview of the machine learning history. The particular issues of modeling machine learning framework is that we want constitutive law to be easily interpretable. But in reality, in particular in the world of solid mechanics, experimental data are actually expensive to obtain. Even direct numerical simulations is actually could be expensive. So one of the major technical barrier is to find the solutions that can allow us to actually use the data sufficiently while able to interpret the results. So here we show some example. One possibility is that we can use neural network to just do material parameter identifications. In this case, we can argue that the model itself is easily interpreted, but then basically that would reduce it into an optimization problem. There's no new knowledge to be discovered. Another possibility is conduct symbolic regressions, which may potentially lead to a new form of solutions, but symbolic regressions are notoriously hard to train, even though they are relatively interpretable. A neural network offers a simple way to train the constitutive law. The reason is that we simply need enough string and stress label and supervised learning, then we can constitute a model. Whether the model is good or reliable is another story. But then the interpretations of the model is often indirect because it's impossible to directly interpret the physics from the weight and the bias of the neural network configurations. So another possibility is conduct model-free approach, which should actually constrain run the simulations without possible interpretations. But then it generally requires a significant amount of data that distribute well into the parametric space. So our goal is to be not to bundle ourselves with the problem here, but try to get to here, where we can create a model that doesn't require a realistic amount of large data, and yet still able to perform well and able to interpret and have the right tone or property of the constitutive law. Okay, so in order to build the neural network, we basically need some ingredient here. Just think of ourselves preparing a Thanksgiving dinner, and then we need turkey, we need gravy, and all the ingredients, and then we start the cooking. So you can think about the learning part is the cooking part, but we need the ingredient that before you start the supervised machine learning, it needs to be ready. And those are the data, the constraint, and the hyperparameter. You need to have a general idea what those are. And then I will go over one by one, and I will go for the method in this talk. The goal of a machine learning task is actually to create a model. So in a traditional workflow, you can see it from the top. If you're working on, for example, a computational possibility problem, you see the stress and strain behavior and also some higher dimensional data or some additional data. For example, dislocation density, porosity, some kind of measurement that are indirectly related to the stress strain response, and you try to incorporate it into our theory. If you are from solid mechanics, you probably would use porosity, fiber tensor as the ingredient into your constitutive law. If you're in other domain, maybe dislocation density, volume of fractions, etc., etc. But in this world, in this approach, your interpretations is actually have to be incorporated into the constitutive model that are fixed. There's no flexibility on it. And you also need to separately identify the material parameter after the solution is generated. And then what we eventually have is the solutions that have the string, have the constitutive model, and have the internal variable set up and then go through the computer algorithm and then get the stress. Here, the important role is the computer. The computer is actually mainly is really work on the computations part of the problem, but not on the thinking part of the problem. So I'm not trying to say that the neural network is thinking, but what we're trying to say is that in the AI approach, the input and output are actually different. We try to have a pair of labels, string, stress, and perhaps some high dimensional data supplement into the learning. And we use the neural network to generate the constitutive law. And then after the constitutive law or whatever computer model is generated, it's supplement back into the first approach such that we can actually now compute the simulations that are in the regular routines. So there is a fundamental difference on a more explicit approach where every detail is controlled by the modeler versus a more implicit approach where we merely try to impose a constraint or whatever criteria that we think the model should have, and then try to use the machine learning to actually reach our goal. So this is actually something to keep in mind. I will start with a simple example to demonstrate the idea. So and if you look at the tutorial that are actually available in the course website, I hope you already done that. Then you would actually get a general overview of the idea. So this is a very simple example. We have the string as the input and the stress as and the energy functional as the output. And if you take the first derivative, you get the stress. If you take the second derivative, you will get the stiffness matrix, stiffness tensor. And the idea is actually using the label to actually predict the response of the constitutive law. So here, one important difference compared to the 1980s model is that the input is actually a string tensor, but then the output is a scalar. So in the classical way, the input is a string and then the output is stress. But here, we would actually only using outputting a scalar. So the important thing is that it provides a level of control you can have, because for the same amount of the training, you can actually use both the energy, the stress, and then the tangents to actually control the quality of the neural network. And that can actually allow you to actually incorporate the data to not only control the quality of the energy or the stress, but also the smoothness of the elasticity response, which is actually important for creating a solutions in a finite element. So this is a very simple architecture. We did not use any advanced neural network technique except just a multi-layer perceptron. And later on, we would actually introduce more exotic configurations. So the first thing I want to cover is the data and the importance of the considerations of how to incorporate the data properly. The naive way is that, okay, I have a string, I have a stress, let's put all the components there, let's pick a random configurations or take configurations of the experiment. Let's say I have a shear test, I just put the epsilon 1, 2, sigma 1, 2 as my input, and then I try to output the response. One thing that are very important is that, first of all, we have a lot of different output, and second, the way that you parameterize the data will make a big difference. So here I want to show a number of examples that commonly used in the supervised machine learning. We actually could use molecular dynamics data, PDE solver data, or actually from experiment. And in some case, we need to deal with the heterogeneous type of data, some experiment with some simulation data, then how to do it. And then there are also data that are of different format that actually make the learning that need to take considerations carefully. In a classical way, you can think about it. even though you deal with string tensor, you essentially treat it as a vector and you put every component as an independent vector and then output a vector. But a lot of data nowadays are available in the experiment are not actually in a vector space. For example, topology data, for example, in this particle can be can have connectivity. So that connectivity is inherently discrete. So if you want to use a discrete data to predict the stress, so you probably don't want to do a classical regressions that actually have a lot of jump in the data. So how do you essentially represent that topology? So you need to consider alternative data format. For example, think about it as a graph. In fact, the technology of the using non-Euclidean data to actually facilitate the learning is a very important topic. In computer science, it's called geometric learning. And you can find lots of information available in the literature. So, and then another thing to consider is that a lot of data are also point crowded. That doesn't necessarily to have a grid-like property. So, for example, this is actually actually material point data on the fragmentations. So how do you actually represent those data to incorporating the model? So this is something that that requires specific technology. There are neural networks specifically for point cloud. So this is also something that new development that need to consider. Another important thing specific for the constitutive law is about how generalizable it is. For example, in many cases, we create one ensemble and then we run the same ensemble with a lot of stress strain curve, with a lot of loading path, and then we create and then we subject to the training. Now I want to actually test the model with a different ensemble, maybe much more loose. Then the training solution is not going to work because this is actually designed for only one RVE. So if you want to generalizing it, then the data demand for that generalization require you to prepare RVE of different size with different particle size, with different void ratio. Then how much effort or funding or support you can generate those data become important issues. And then we need to think about how to navigate the way to explore the data space. So in this case, a pure supervised learning would not necessarily work because the data demand you to compete the model is so enormous. We need a better approach so that we can have a more effective sampling, which we will cover in the in the lecture 4 of today's lecture. So this is actually the data situations. Another possibility that we can think of is that if the data actually does not marry with a lot of noise, and we also have experimental data that are available to calibrate sufficiently a high fidelity model, is it possible to combine the simulation data from the direct numerical simulations and also the simulation data to actually create a database that allow us to actually compete the training? So this requires us to actually control the data and then give different preference to the different level of data. In this particular case, we have a loading task in the piping, and then we load the tests in different directions. Only a subset of them are true experimental data. The other type are actually the simulation data that are using high fidelity model. So in this case, discriminated objective functions that emphasize one goal over the other are possible, but how to tune those hyperparameters could be difficult. Could be a problem that I actually need to explore. Another important factor to consider is actually the correlations and the causality of the data. We have another type of, oftentimes we have data more than the stress strain. And then those data come as a time series, like porosity, fiber tensor, or actually some kind of connections that are obtained from the image. we can create a lot of different parameters. So if you think about it, when we create a learning problem, it's important to consider the causality and then those parameters. So in this case, we need to actually making sure that we actually predetermine or actually at least understand the causality among different data to put it into the right learning problem. In this particular example, this is actually the training of a granular matter. We try to predict the stress from the string, but then we have a lot of data. You can imagine that everything is stored in an Excel spreadsheets with void ratios, density, or dislocation measure, graph connectivity, everything. You can imagine that in an Excel spreadsheets, which one should be input, which one should be output, should we put it randomly? This requires us to figure out what is the relationships that cause something change among the other. And there are also ongoing work on the causal discovery among the data that can create something called a causal graph that represent these relationships. So in this case, it creates ability to help us interpret the model and also to recover to actually create the predictions that are consistent to the physical mechanism. So this is actually the part of the data that required to do the training. Again, the supervised learning is actually very simple, but how you actually formulate it can make a big difference. Another part that I think is very important is talking about the constraint. Okay, so in the classical way, basically what most of the people did is actually they would actually have a string as an input and output the stress, and then they're minimizing the stress in terms of some usually L2 norm, and then you just create the solutions. Okay, so yeah, you may want to ask whether this is a good approach or is it sufficient? Or if it's not sufficient, we probably need to impose more constraint. Then how to constrain it? So here, I just repeat what we already showed already. We have multiple choice and those choices need to be justified. We can only constrain the energy in this particular case. We can also control the stress measure and the stiffness, and we can bundle it together. It would actually lead to a different type of loss functions and the loss functions in the supervised learning tell us what is the goal of the learning in a mathematical sense. So here in the first case, we simply try to minimizing the energy. In the last case, we try to create a neural network solutions that not only give us a good stress, the stress measure, but we want to make sure that the straw energy and then the tangent are actually correct. So in this simple case, we can see that adding more constraint together doesn't hurt the other constraint, which is actually indicating that the multi-objective solutions is not in conflict of each other. So what you can see is that if I actually add if I purely use the energy to actually change the error, I get a type of profile. But as I add more constraint to the stiffness to control also the stress and the stiffness, I actually did not need to sacrifice the quality of the prediction of the energy, but the stiffness predictions and the stress predictions is actually improved significantly. I think that also indicated that the underlying true learn function is not is actually have some smoothness there, so that the pattern that you actually generate can actually easily constrain. But this is actually a trick that playing with changing the norm with a high order norm, and then that create more control on the resulting energy functional. Particularly important for creating a solution for implicit finite element or implicit solver that requires smoothness. But I also want to emphasize on the other type of constraint that are often not incorporated in the supervised learning. One case is the incomplete data, okay? So if you want to train a stress strain curve, but you don't have any energy measure, is it possible? So here we actually introduce another case where we actually only have one energy data, which is actually when the deformation is 0, there is no energy. And then we try to create that constraint. And notice that because we actually have one point that actually control the stress data, this is sufficient to recover the stress data. And this is actually H1 energy function training with incomplete data on the energy data. So what it shows is that in this sense, you don't have the same amount of the data on each type of the objective. But another type of the training that are particularly helpful on training of constitutive law is also the physical constraint. So here we show 3 examples. If you're familiar with container mechanics, that should be pretty obvious. This is to train the large deformations constitutive law, a hyperelastic energy functional from HMX material, HMX crystal. We can see that we can add a constraint there to enforcing that if I rotate the observer, I should not change the energy and then the stress and then the tangents predictions. And so Q is actually a rotation tensor that allow us to check whether if I rotate the current configurations observer, whether I can get the same response from the mechanical principle. This could be converged also into the training part. And then also similarly, the symmetry requirement. Lots of time when we train a constitutive response, we may directly using the invariance approach to actually create energy functional that are of the right symmetry and also make the simulation easier because we probably will have less input. But for very generic predictions, you can actually impose the symmetric loss functions. And shown here is actually the comparisons of incorporating the loose functions, the symmetric loss functions in the supervised machine learning problem and not putting it. You can see that if you don't enforcing it, even though the material data is actually have symmetry, in this case, monoclinic, the resultant data is actually the resulting prediction lost the right material symmetry, which could be a problem in the numerical predictions. Another important thing is that to consider is that when we actually conduct a supervised learning problem, do you want to impose all the loss function in one step of the training, or you want to do it sequentially? So here we tried a different approach, in which case, and this is actually very empirical, but we find the success is that we may actually first conduct sublab training that doesn't impose those additional constraints to get us into a good behavior, and then conduct a transfer learning or correction approach, like a predictor corrector approach to introduce additional constraint to help us make minor changes of the resulting learn function such that it can obtain all the desired behavior. So what I want to show here is that the objective is not absolute, and you need to think about what is the right way to imposing it, and then it will lead to a model that are more robust. In this case, if you don't do anything, there's no symmetry, and you may even lose the material film indifference, even though the stress strain curve may look like it's really good. There are also another more complicated things that we need to consider. For example, when you train an energy functional, you may want to impose that it has a strong ellipticity. So this could be done by calculating the acoustic tensor first in the second order tangents, and then compute the determinant, and then you can put it in the loss functions. But that could actually could be really complicated. So you need to think about whether all the constraints should be putting into the training program, or you can actually first train it and then get the solutions and then check whether those constraints are actually satisfied. So in this case, I would say it's problem dependent and will probably require some tests, but the property like strong ellipticity, if your data actually obtain the strong ellipticity, you may not need to put it into the training, but rather you do a post-training validation program to ensure that all the properties are met. So there are also another criteria that are not continuous. I want to emphasizing that not all the criteria can be described as a smooth functions. This could be important because when we tune the neural network, typically we need a gradient. So, but there are also criteria that are discrete. So shown here is a simple example. We have a polycrystal and then we label it, and then we actually use some technology to create a representation of that polycrystal. But I have to label those polycrystal with a name 1, 2, 3, 4, 5. If I change the name, if I swap the order, the name, I would get a different degree of connectivity matrix, different adjacency matrix. However, this is still the same polycrystal. So in this case, how do we need to actually ensure that permutation invariance is also fulfilled? And this can be done in the neural network level, where we basically have neural network that inherently obey the invariance property, or we have to do it in by actually creating additional data. So in this case, simple problem, we're showing that changing the label of the microstructure in individual nodes in the microstructure basically lead to very similar results. Another important thing to consider is when we want to incorporate the microstructure directly inherit from the convolution neural network into the predictions. So here, this is a tensor, a second order tensor in particular, that are actually graphically represented, and this is actually the microstructure that are actually obtained from a porous media. Okay, one thing you want to try if you're actually already working on the convolution neural network to create constitutive law is that try to rotate your image. Okay, try to rotate your image and then actually create a rotated label and see whether after you train, you obtain the same training with different orientations of that same image, you get the same training response. If not, then it doesn't have the equivariance, which I suppose is important. So this is actually done by our collaborations with the UC San Diego colleagues. I think this is a wonderful work. It would be better if we cite more paper, but but the equivariance is an important issue in incorporating microstructure. Okay, so we have all the ingredient, we have all the constraint, and we can constitute a problem. But then we can also represent the loss function in many, many different ways. This is something that I actually was quite surprised that almost none of us, sorry, not none of us, but the majority of the work, we cannot find much exploration on that, is that how do we parameterize the problem properly? That can actually make the training easier, okay? So this is actually inspired by my colleagues' work from San Diego. This is actually basically a very simple optimization problem to find what is the singular point of acoustic tensor. So we basically need to rotate the orientations from to create a different acoustic tensor for the same tangents of the constitutive law. But this is actually the interesting part is that if you rotate, if you represent that rotations in a different way, you would get a different problem of very different difficulty in your training. So this is actually the color, and then the z-axis is actually the loss. You can think about it as a loss functions contour, and then the x and y are the parameter that control the angle. There are multiple different ways to represent a rotation, but if you actually make a choice out of 4 of them, so let me actually ask the live audience there. If you want to solve a supervised machine learning problem, are you going to choose A? So we're mainly represented with the Euler angle. So do you think this would be easy? or do you prefer to do B? Okay, so B is nice. I mean, there's only one potential, there's one minimizer. No matter where I am, okay, I actually, if you know the optimization part of the machine learning, I always get back to that point. Actually, A is not too bad, but you have to deal with the fact that if you're somehow at here, then you may have a hard time. Should I go this? Should I go there? Okay, but C and D will be much harder. So as you can see here, you deal with a settle point. But then the thing is that the interesting thing is that this is the same problem. Okay, so how you represent it? Yeah, so sometimes the first thing when you train a neural network doesn't work is that maybe I use one more neural network layer, add more neuron, but you may want to think about your objective functions that actually change the difficulty maybe by 1 or 2 order, if you think about it carefully. So that also go on the mathematical part on how to represent your loss functions. So I will actually show an example like what we did before. This is actually on the collaborative work with our colleague, Dr. Haider. So we can represent, in this particular example, we can represent the rotation part of the deformation gradient. We can measure how good it is, the constitutive law predict passing flow directions with 3 different representations. Okay, so the 1 is the ground truth data, and then the 2 is actually the prediction from the neural network. We can measure the difference using the Euler angle because you have 3-dimensional orthogonal basis, and you can actually compare. This is actually the true orientations, and this is actually the prediction. What is the discrepancy between the rotations? That is actually legit. You can actually check if the rotations part is actually lead to that property that are actually necessary for correctness. So if our rotations, the inverse is actually equal to the transpose. So if R2 equals to R1, this norm would be 0. So that is actually also legit, or you can use the Lie algebra. One thing that I want to test is that we also have material data that can actually have a change of orientation very quickly. In this case, the crystal plasticity. So if we train it component by component, this is actually what's going to happen. Because the data is actually a crystal plasticity data, it can actually have a slip system getting activated, and then what you can see is that you may lose the slip because the parameterizations in the component-based training is actually not very sensitive to the onset of a sudden slip system, of a sudden rotations in your tensor. But in the Lie algebra, this can be tested that actually allow you to capture the slip system activations. So in general, we can impose all the criteria we think is necessary to train a constitutive law. But then what you see is something similar to here. This is actually done by my other PhD student, Bahadur Banmini. Okay, so we can actually, this is the inverse problem in which we try to create a conductivity tensor, predict the conductivity tensor. I can add all the constraints there, but then the problem is that whether we can solve the problem because in general, if you actually only try to minimize the stress strain curve, you actually have a single objective problem. But here, what you want to do is that we want to actually recover we want to match the experimental data, but we also want the conductivity to be positive definite. This is actually a physical requirement. We want it to be symmetric. We want it to have all the property, but then it needs to multiple objectives. One thing that we need to consider in the training, and that is actually very important, is that in the sublet training, we actually seeing that adding more constraint actually make the training easier because those constraints are not in conflict to each other. A situation where when you take the gradient of different objective functions, they are aligned with similar directions, if not identical. Probably like case B, even with some scaling problem, or case A, that adding more constraint doesn't necessarily kill the problem, But oftentimes we are dealing with conflict. So in life, you also deal with a lot of conflicts. You want to study an exam, but you also happen to want to have a party, and then so that create a conflict situation. So should I spend 1 hour study and 1 hour go to the party so that I can both not study well and also not enjoy the party? Or should I do one thing first? Or should I actually just go to the party and don't worry about it? Okay, so how do we deal with the conflict situations? Mathematically, we need to deal with that. And as you can see here, one constraint when we take the gradient would actually tune the way and then a bias towards these directions, another one towards these directions. If the classical way is that for different objective, we are going to put a way into different objective, but then that would actually create a compromise solutions. It depends on how important you think this thing is. I do a little bit of something. So when you write a constraint, you also need to think about what is the right way to impose that constraint. One possibility is like what I'm talking about. Maybe I forget about enjoying the party. I would just focus on study first and then see how much time I need. And then I deal with the party later on, or I can have fun first and then deal with the party. So that can be done easily by changing the norm, because you don't actually need to use the L2 norm for the multi-objective. You can also deal with it in the transfer learning example that I just provide. You can change a set of the criteria first, and then train another part of property. Or another possibility is the following. Because your gradient is multi-dimensions, so even in this particular case where there is a conflict solutions, I can still do this thing a little bit better by actually only propose a direction that are in that gradient directions, that orthogonal directions, so that I can do a little bit of these tasks better in one directions and forget about the conflict and then deal with the conflict solution later. So how does it work depends on the true landscape of your value functions, because it's really hard to see which way you may accidentally. In principle, it's also possible that you just randomly put the initializations and then you actually get the solution without loose functions. So, but what actually happened is that during the training, you may explore the landscape of your loose function differently, and that can lead to different results. So this is some empirical research. I just want to show there's some success in that regard on using the gradient surgery. The gradient surgery is not invented by us, but by the CS colleague from Stanford, published in 2020. You can see some improvement. If you just do a pure pin, we get a pattern quite far away from the analytical solutions in a pin that may be not well designed, I would say. But in the gradient surgery, if you actually perform that, we can see a significant improvement also on the loose function profile. So one thing that I want to perhaps demystify is that the way to think about the constraint is very important. Okay, and then the way to actually achieving it requires some careful thinking. Don't use L2 norm all the time, and don't put the way randomly. This is important because in mechanics, basically all the criteria that you impose is really hard to say which one is more important. Matching the experimental data or get a positive definite elasticity modulus or whatever. Can you put a weight on it? So I guess it's really hard. So it's like in life, a lot of time you say everything is important. What is truly important? They're all important. So instead of making one compromise for the other, try to find a solution that make everything and everyone happy would be important. Okay, I want to talk a little bit about hyperparameter. This is also something that very important and very time consuming. When you write a handcraft constitutive law, you don't deal with hyperparameter, you only deal with identify the parameter. So this is actually great. So here I would consider hyperparameter as any parameter you require to complete the training, but that has no physical meaning. Okay, so there are other more rigorous definitions, so I'll stick to that. This also require, again, considerations. There's no good way to solving it. Here, we just show some example. In general, the problem is not that you don't have enough choice to constitute a learning problem, you have so many choices that can do things more or equally similar. So just for example, to train a neural network that have some simple plasticity, I can do gate recurrent neural network. I can do multi-scale feed-forward neural network. I can do a 1D concurrent neural network. Maybe you can, one possibility is that you write one paper for each of them and then cite each other too. But you somehow also know out of these all possible configurations, there may be some configuration that marginally or significantly better than the other. So you also need to think about how to explore the space of the hyperparameter functions. So here we have some work that are not necessarily the best. I think that the best in the thing that the training in the industry is to use the Bayesian's hyperparameter tuning. But here we do some, but here we consider the problem where we already know some of the choices are probably good. And if you think about it carefully, what we're going to do manually is that maybe I just train it multiple times. Okay, I will train an LSTM with my favorite hyperparameter. Maybe you just put 2 layer neural network and 100 neuron per layer and see what happens. And then I just pick the one that are good, then publish in the paper, and then ignore the one that doesn't do well. Okay, but we can think about it more rigorously. If you want to exploring it, you can use a recurrent neural network to actually write down all the decisions you have that lead to a decision tree. So here is not exclusively all the possible way to build a black box neural network, but just some example. You can use multi-layer perception with multiple layer, or you can actually consider how many hidden layer you want, how much neuron, the brush size, the dropout weight optimizer, and then the type of activation functions. One possibility is that we can use the neural network to actually find out which path is more promising. But there are many other ways. The thing I would not accurate is that manually try everything. I just want to write it out because if you think about it, even with this limit choice, the possible walk in this decision tree could be quite time consuming. If you're a graduate student, you definitely don't want to try everything that are available unless you have a lot of time. But I won't recommend it. Okay. Another thing that I probably emphasize too much by now is actually also your activation functions have would actually affect the derived property of your learned functions. So continuity is one thing. So this is actually a paradox because a lot of literature are in the RE-LU activation function because it's simple and you basically can find more support from the RE-LU, but it's not continuous. It's actually basically not suitable for the higher order sober training. But then you want to take advantage of the good theoretical result of the RE-LU instead of using an exotic one. Then what you probably need to do is to think about how to design the neural network. So this is actually something done again by my student Nicholas Vanes on up higher multiple layer. So design just a multiple layer to increase the degree of continuity such that the results of the REU can be used. Now here the problem again is the choice. Because I may not want to use LE-LU, I may just use a hypertangents or anything that have more continuity. Okay, so how to find it is actually something that there's no clear answer, but you may want to consider or actually conduct a hyperparameter training. I want to emphasize that I think the role here is I would say that compared to the finite elements or the classical way to write a constitutive law, writing a neural network constitutive model is a little bit less established, or maybe even the supervised learning. We know much less about the space or the kernels or the metaphor of the solutions it can produce. But there are increasingly more theoretical work that can guide us on how to create a neural network. So here is one of my colleagues' recent work from what is the approximation power of the 2-layer neural network, which is actually, you think about it, this is kind of encouraging because it tells you what is the number of neuron per, if you actually fix the number of neuron way is actually 2. Okay, and I have a function that with some level of, if I have a function that with certain property, what is the number of neuron I actually need per layer in order to fulfill the approximation task. So the work is there, but sometimes I would say this is like climbing a mountain. Sometimes the tool is just not there and you just have to wait for other that actually install the tools. But I think the future could be promising. I want to talk about 2 advanced topics for this first lecture, and I will end it. The first thing is actually the incorporate of the non-Euclidean data, in particular the things that have a discrete nature. And there are many different ways. I just talk about it represented in the graph. So this is actually the granular material that you can actually see. Okay, the stress is actually not just due to the whole thing actually gets stressed, but the contact. And the contact is keep changing. If you have shear or you actually rotate, have torsions, new contact form, and then that topology is actually the change is actually one of the reasons that we see complex behavior. So one way we want to incorporate a more physically driven or actually more physically consistent way to actually model the problem is to incorporate the topological structure representing the graph to do the learning. So the graph representations in mechanics is actually nothing new. So you can, if you can use the when you generate a polycrystal inherently, you create a graph because you can consider the graph is basically a triple, sometimes 2 triple, sometimes with label that could be multi-triple. But what it means is that it's basically a way to represent the data that represent relationships. Okay, so not all the material have complex relationships. Like Facebook, that friends network have complex relationships, but some of the material, a subset of them, their physics is actually manifest from that change of the relationships. In this particular case, I would actually consider a sample. Doesn't matter what the ensemble is. And then we have individual entity. In this case, this is a particle. And then if they're connected, I would actually assign an edge to it. So that create a network. The important thing is that we can also assign property now separately into the nodes and into the edge to represent the data in a way that emphasize relations. You can think about it in the analog. If you can predict the overall community, how much people willing to take vaccines by actually looking at the Excel spreadsheets of each individual persons, how old they are, what is their education level, what is their political spectrum, whatever. You can do it in Excel spreadsheets in a Euclidean data way. Or you can do it in a Facebook way where you represent that personal relationship in a graph. So this is friends of each other, their wife. Okay, this is, I don't know, this is the student of that person's. And then you can assign attribute. For example, the person that are very powerful or actually is a fake news spreader. And then, okay, you can assign relationship to that knowledge graph. And I can tell you in many cases, if the relationship is important, you have a more effective way to actually make a more accurate predictions. And this is actually underlying the philosophy of using the graph to represent the data instead of the Euclidean basis. So that being said, I won't recommend that if you have a grid-like data that have no special relationship, then using the graph to represent the data may not lead to that much benefit. So this is one way. Another way to view with it is that we want to actually distinguish something that if you're doing it in a classical way, we would actually have the same descriptor. Okay, so this is actually like, for example, I want to model particles C, assemble C and D, and if they have the same porosity or same void ratio in the effective medium level, they're identical. So, but you don't want the constitutive response to be identical for these two things because you know it's not precise. Okay, so what should you do? then you need a new control on that data. Okay, you need a handle so that you can distinguish C from D. And then this is actually where the graph configurations can do. So the training is actually, in this particular case, very simple. And that actually helps us also generalizing the data. We have a polycrystal. So in this case, I just use a polycrystal as example because I have enough interesting response, but it can be done in any other assemble. We have a polycrystal, and then those particles are actually and those polycrystals are actually assembled in many different ways. And then we actually do a direct numerical simulation from the FFT and then create a database of different topology that create a assemble with the same size. And then with that label, we would actually use both the graph as an input and then also use the stress strain curve as an input as the data for the training. So that leads to semi-supervised learning architecture where we would actually use the graph as the input, but we would actually use unsupervised learning to create a low-dimensional representations of the graph data. And then this would be served as the additional input to help us to change the energy functional when we generate different microstructure. So this is two example. We have a assemble A and B, and then they are actually have a different encode feature vector to represent the microstructure. These encode feature vector are used as the additional input, and you can see the energy functional. Okay, because they are, even though all the property actually look the same, but because we actually have a different encode feature vector as an additional input, then we can actually create a different energy functional that is specific for a new specific type of microstructure. So that generalized the learning problem, because previously we would be focused on one RVE creating a predictions, but here we can tackle a family of RVE, which make the predictions much more generalizable. The price you pay is that if you want to generalizing it, you need more data. This is actually, I mean, this is actually kind of trivial. Okay, so the more general you want, the more data you need. Okay, so and we can actually make create also tackle the elasticity and plasticity. I think I'm kind of running out of time, so I probably need to rush a little bit. But maybe in 10 minutes, I try. Is that okay? So I probably would let me go for that, and then I would get the track questions. So, but oh, 5 minutes. Okay, I will get it done. Okay, so sorry, I think. Okay, so this is actually one way. I just want to show that data structure on the polycrystal. So this is a very simple problem where we have a sample of 5 particles. We have a degree of connectivity that tell you how much, how many neighbor does each individual particle have. And then we can compute an adjacency matrix, which indicate which particle is the neighbor of each other. And then we can compute a graph Laplacian, which is just D minus A. Okay, so this matrix actually represent the microstructure. So we can actually convert the representations of a graph into a matrix form, and then individual feature of the nodes and then the edge can be put into in the feature matrix, in particular if the graph is used. Because of the lack of time, sorry, I spent too much time at the beginning. So I would probably just go for this very quickly. So we would actually try to use the encoder part of an autoencoder to create a compact predictions of the polycrystal, and then we would actually predict the constitutive response. Another possibility of representing to incorporate the microstructure is to consider the transient change of that microstructure as a way to capture the change of the graph. So here we show some of the results where we show the particle are actually a granular material are actually getting deformed, and then the particle are actually have a microstructure revolutions. And these microstructure revolutions are actually embedded into a vector space, and then the change of the microstructure are actually represented by the change of that vector. So that you can think about it as a compaction of informations. And the nice thing about this is that because the graph is now represented into a very compact space, this could be incorporated as an internal variable for our modeling, and then we can actually see the response data with the checks with that allow us to generate predictions that are consistent with the change of the microstructure. So we use a technique that converts the graph into a vector, and then that graph data, the revolution of the microstructure are additional data used in the training, and you can see the training and the test data are aligned with each other. This is actually some of the stress string results that you can see. Seeing that the microstructure can actually help us predict better stress string response even in the three-dimensional case. I really don't have time, but maybe I would just outline the fact that if you want to extend the idea to plasticity, we can actually not necessarily just simulate it with a stress string approach. We can actually impose still more entity that balance the ability to have a very general predictions to something that that actually have a physical response. So I won't actually talk about the details, but then the main idea is that we can all consider the yield functions as a level set. And then that would be a most general way of consider yield functions. And then we can use data to govern the Hamilton-Jacobi equations so that we can actually get stress, get a very generic constitutive law. I think in some sense this is exciting because it merged all the plasticity model into one meta model. Not all the plasticity model. All the plasticity model that have yield functions can be merged into a macro meta model where in individual plasticity model are just special case of this general meta modeling framework. I won't go over the details, but then the key is that the level set is actually trained from the stress string data, and here we can show some special case where the classical mathematical framework actually can be recovered easily with the neural network data. I know I'm running out of time, but I'll just stop here. I just want to show some of the response where you can see that with the framework of the model-based neural network that have a yield functions, we can create a more robust response where you do not see the oscillations for the cyclic loading. This is in particular advantage for the data that have a lot of cyclic response, where the neural network or LSTM or the gate neural network may actually lead to some buckling response or some local oscillations. So I really would actually conclude my talk. I just want to say that in general, the ingredient effects is, again, it's like a Thanksgiving dinner. We already have all the turkey, everything that are actually set up. How we cook it is actually a matter of in our hand. And then there are many, many different ways to cook it. And this is so confusing. But I think there's some general guidelines. There are some general good principle or practice that I hope that I can actually present my own point of view. By no means is fair, but I hope that that can stimulate some discussion and thought. By no means I think that I did it in the best way possible, but I try my best to do it. Okay, it's like a training problem without absolutely controlling the loss function to zero, but you may find a better way. So with that, I would give the stage to our next speaker. So thank you. I would, because of the time limit, we may delay the discussion later on, and then maybe before the break, I will answer the question. Thank you. So the remote audience, can you come back in 10 minutes? So we will have a short break, and then the next lecture would continue. Thank you.